Good morning, everyone, and welcome to another live Quanser user webinar. In these webinar series, we highlight the work of academics around the world that use Quanser solutions and technologies. My name is Michel Levy, and together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today, I'm really excited to have a great friend of ours and actually one of our first ever clients, Professor Brian Armstrong from the University of Wisconsin-Milwaukee. Professor Armstrong studied mechanical engineering, physics, and electrical engineering at MIT and Stanford. Since arriving at UWM in 1989, he's taught circuit analysis, controls, and embedded computing to undergraduate and graduate engineering students. He's published 2 books, numerous research articles on robotics, controls, and image metrology. Professor Armstrong has also co-launched and led a startup company called Mitra Innovation to commercialize a 3D image metrology technology that was developed in his lab. He's also been awarded 22 U.S. and international patents. So today, Professor Armstrong will discuss how they use the Quanser Rotary Servo in their control systems lab to teach system identification, modeling, and control design techniques, but in a very unique way. So I'm looking forward to that.
Okay, so as Mitch said, and thank you, Mitch, for that introduction, I came to UWM in 1989 and began teaching introductory controls. Shortly after that, my colleague and I, Ron Perez and I, we won a small internal grant, or maybe not so small, but to build a controls teaching lab. And so that was 1993. Our objective in the design of the laboratory was to maximize discovery learning. We wanted to give the student as little prescriptive directions as possible, and to the extent possible, leave it up to the students to design the experiments they would do to reach objectives which were centered around system identification and corresponding controller design. So we developed a sequence of labs where each has a progressively more elaborate model than the preceding ones, and correspondingly, that more elaborate model of the plant allows the student then to do more elaborate control. And as the modeling becomes more sophisticated, by which I mean really starting with a very basic model of DC gain, and then going to a single pole model for dynamics and transient response, and then finally to a fourth order model. As additional features of the response become visible, then at that point along this journey, they are considered in more detail by the students. Here's a picture of our early apparatus. So for those of you who jumped on the bandwagon early, you'll recognize an SRV-O2A. We actually had an SRV-O1 for a period of time for evaluation. And then here's the amplifier unit, and you can see the breadboard that Jacob talks about in his webinar as kind of being the earliest approach to controller design. So if we go all the way back to the beginning of time, there was a conception of that analog control circuits would be built up on this breadboard. And of course, things are very different today. Okay, this slide got to be a little bit busy. Let me just say that there are 7 labs. We execute the 7 labs in 14 weeks with some review sessions for exams done during lab periods. Some of the labs are 1 week. And as we talk through these, basically I'll present each of these 7 labs individually and speak to them briefly. We'll see that some of them are shorter than others. And so the students work through this progression in 14 weeks. when we purchased a kit of SRV-O2B servos, when we updated our gear from 1993 vintage to 2017 vintage, of course, the controllers now are built in Simulink, and so we added a lab at that time, which is an introduction to Simulink. The students start out in controller design in that introductory experience just by cut and try, just by changing the gains in order to achieve a performance specification that they're measuring by observing step response plots. Okay, so let me advance here. This is talking about that first lab. The lab itself was adapted from controls tutorials for MATLAB. Our goal is that students will get started with Simulink. And so in their preparation for the course, students have a background in transfer functions applied to signal processing. They're just beginning in this with control theory in this introductory controls course. And we're not assuming that they're familiar with Simulink, although some of them will be. I'll also mention students work in groups of two. And so doing that, you get a mix within each group of skills, and so that may bring in some additional Simulink experience into each of the groups. They set up, as you can see, a pretty simple system. Get started with the scope to be able to capture data, and they play with controller gains and achieve various characteristics of response. So the next lab is their first lab on the hardware. And I'll mention that the lab manual is almost 190 pages. 2/3 of that, I would say, is tutorial material. And I'm a great believer in presenting students with kind of the raw, unfiltered information. So we talk quite a bit about the sensors and what their characteristics are. So mechanical introduction, we see the 3 sensors there. They collect data on each of the sensors and characterize the sensors. Then proceeding to lab 3, we developed the first, rather a more detailed model of the SRV-O2. And this model is a characterization of the steady state volts to velocity relationship. And so you can see you can see some measurement noise, some measurement issues here. You can see that the volts velocity relationship is approximately linear with this nonlinear dead zone arising with the friction. And so they'll collect data that allows them to establish these points, and then they measure or they identify rather the DC gain for the system. This, first of all, it's illustrative of this idea of starting basic. We try to give the students as little as possible, either in the form of data and characterizations that they just accept, or in the form of detailed steps and sequences to follow to the measure of the data. So we introduce them to the basic hardware in the loop blocks that are part of Quark, and away they go. They get an indication that they're to map out this voltage velocity relationship, and they do. Another point to make on this slide is that we're not yet into the time domain. There's no transient response here. So even though these curves are a little suggestive of that, this slide is talking about, or this figure is talking about linearization, which is part of handling this data. So we get to lab 4 and finally do some control. So in lab 4, they implement open and closed loop controllers. And here again, we're trying to be very basic. So the closed loop controller is just proportional control. It's a volts velocity relationship. And the and so the and then we talk about some of the basic advantages or utility that arises or that can that's achieved with feedback control. So they look at transient response and rise time with respect to loop gain, and of course the system gets faster. We have an approach to introducing parameter variation, namely we put an additional resistor into the circuit path for the motor, which changes the motor characteristics. And then we look at how feedback control gives robustness to parameter variation. We introduce a disturbance. We do that by having them put the motor servo on its side and offsetting the link so that there's a gravitational torque. And so the students measure the effect of this disturbance, and then of course see that increasing the loop gain mitigates the impact of disturbances. Okay, progressing. Well, hardware modifications. So at this point, I want to talk a little bit about modifications that we have done to the hardware. A first modification is to introduce resistance into the motor circuit. And throughout the semester, the students run with a first resistor, which is 2.5 ohms. The motor itself is 2.6 ohms, so it approximately doubles resistance. And our motivation for doing that is to increase the open loop time constant. So a stock SRV-O2 has an open loop time constant of 45 milliseconds. And with two modifications that we do, I'll mention the second one in a moment, we increase that to 300 milliseconds. Our motivation for increasing the open loop time constant is that we want the student to be able to perceive that the motor servo gets faster. And if it's so fast that it's at the limit of human perception, with a stock SRV-O2, if you put in a step change in voltage, velocity changes what appears to be instantly, and it changes in 50 milliseconds, but the human has some difficulty to perceive that. And actually, the unit itself makes a bump sound. It goes bump, and it's turning at a different speed. And you change the voltage again, and bump, it's turning at a different speed. And so while we know that feedback control can make slow systems faster, and of course, we can collect data and make plots. If the system is as fast as 50 milliseconds, it's not possible to perceive that. And at the very root of this, having a piece of hardware equipment like the SRV-O2, the objective is to visualize differential equations for the student. So we want things to be perceptible in the hardware. You make a change in the control, what the hardware does changes. And of course, we get that in part by slowing down the transient response, and then feedback control is able to speed it back up again. So the two changes we do that have the effect of increasing the time constant, the first is to introduce this resistor. We get about a factor of 2 increase in the time constant from that. And then the second is to change the link. So here's a link that we made here at UWM. I think we manufactured these, or Quanser may have made them for us. And here's the original link. The new one is steel. The original one is aluminum. And we get a 6 or 7 to 1 increase in the inertia. So the combined effect of those two changes is this increase in the time constant. A second change that we made is to remove the gear drive between the motor and the main shaft and introduce a belt drive. And the reason for doing this is to introduce a flexible mode. We'll talk about that in a moment, and we'll be able to see that in some video coming up. And there's kind of an interesting motivation behind our choice to introduce this flexible mode, but which I'll talk about as we get a little bit further on in our discussion. So the belt drive is there. All of the units have the belt drive installed, and it introduced a lightly damped pole pair, which is quite stable across the units. It's got a resonant frequency of about 35 radians per second, or about 6 hertz, and a damping factor of, actually off the top of my head, I'm not sure of the damping factor. Let's say 0.1. It's relatively lightly damped. Okay, so as the labs proceed, we get into lab 5, dynamic model and PI control. I should mention the synchronization between the lecture portion of the course and the labs. The two are not closely synchronized, although when I give lecture, I frequently draw upon something that I know the students are seeing in lab, and so I can tie the mathematical development in lecture back to what students are seeing in lab. We're in the 5th out of 7 labs here, so we're getting quite far along. And for the first time, we're introducing a model of the plant with a pole in it. The students in this lab develop a first order model looking at transient response. Here you see transient to a square wave voltage input. So we have a first velocity and a second velocity and transients between them. We have some MATLAB fitting tools, so students don't need to develop an expertise in the nonlinear fitting problem of estimating rise time constant in a least squared sense. That is one of the things that we do for them. But they'll measure a time constant out of this transient, and then from that get a first order model of the plant. Recall that we're still working in voltage velocity control, and we'll using that engineer a controller by pole placement. And in terms of the synchronization with the course, I think as many or perhaps most introductory control theory courses will do, our course starts with discussion of modeling tools, builds up the basic mathematics, as well as tools to estimate controller performance metrics such as rise time, settling time, and so forth out of transfer functions. And so even though we're in the back half of the semester, by the time we get to lab 5, that's appropriate, because the second half of the semester in terms of lecture introduces controller design techniques. So this first controller that the students do, they design using a pole placement technique. Now, a second thing that we introduce in this lab is frequency analysis. As you'll see when we turn to lab part 6 and finally our capstone, lab part 7, frequency analysis plays an important part for us. And again, system identification is this long-running thread in the sequence of labs where they start with a very basic model that incorporates DC gain. At this point, lab 5, they're working with a model that brings in that first order transient of the motor servo, and then we're going to progress to a more elaborate model identified with frequency analysis methods. And so to get them started with frequency analysis, we have them measure the tracking error as a function of frequency. And so they will apply sine waves. I think this might be the input signal here. The the red, and then this is measured data with a fit. Where we're measuring velocity data, so you can see the influence of the tachometer cogging. And this would be a typical data set that students get. In fact, this plot may have been made from actual data. And so you can see that by measuring the magnitude and phase of tracking error at various frequencies, students can identify the closed loop tracking error transfer function, and also it makes a good basis for discussing bandwidth for the system. So the students can see that at low frequency, the system is very accurate, and then it begins to lose accuracy as the input frequency is increased. Okay, so our next lab, Lab 6, is devoted entirely to system identification. It's really preparation for the competitive tracking challenge, which is Lab Part 7. And the students will, first off, begin using the system observing its position variable rather than velocity. That, of course, introduces an additional pole at the origin, and we'll measure the frequency response of the system, voltage to position across a range of frequencies that's sufficient to capture this, the resonant mode introduced by that belt. And the data set is the same between the left and the right here. Let's look over here on the right. You can see this rapid shift in phase, which corresponds to the frequency of that resonance. An issue that arises in this frequency analysis and modeling is determination of the number of poles and zeros. And that may be one of the most complicated issues that students deal with in lab during the semester. So the handout, the tutorial materials, which are in the handout, are a bit lengthy, and but walk the student through why there's a determination has to be made of how many poles and zeros are identified in the data. And that's actually what you're seeing in this figure. This is a figure from the lab handout. On the left, we have 4 poles and 3 zeros, and on the right, we have 4 poles and 1 zero. And there's a discussion of avoiding overfitting the data. Here we see a clear example of overfitting. The data ends here at about 300 radians per second, and up here at about 500 radians per second, we have this dramatic phase shift feature, which the data doesn't support. And so we make the case in our presentation that even if you have a smaller least squares fit residual with this more highly parameterized model, that the data is not supporting this choice of this more highly parameterized model, that the simpler model is the preferred one. So Lab 6, the students work through all of that. Again, having the MATLAB Simulink environment as opposed to the homebrew controller software tools that we were using in 1993, gives us a very straightforward way to collect data, to set up the students to analyze data. So I said at the beginning that we wanted the students to be working from scratch as much as possible. That concept applies to measuring sensor response characteristics, observing, calibrating the sensors, and everything that's done with respect to the control. But with respect to the data analysis, data reduction, and so forth, we've given them a number of automated tools that operate in MATLAB, which help them then to complete this analysis. So all of that brings us to the capstone. And let me switch now to some videos that I have. And I'll explain what our capstone challenge is. So we take two SRV-O2 units and set them up in a target tracker configuration. We could call this leader and follower. And the one on the left, I control. The setup is position controlled, and I put in a reference signal, which is a multi-sign signal that accelerates over time. So the left-hand unit is going to move faster and faster as time goes by. The right-hand unit, the student controls, and the signal input to their controller is the instantaneous position signal coming from the target. We call the student's unit the tracker. And as you'll see in this video, it's set up then in a target tracker configuration where the tracker follows the target. There you can see that resonant mode, the lightly damped mode. Okay. And now flicking to this second video. So here it is with the trajectory being generated. It starts out rather slowly, as you can see. It's not purely a sinusoidal motion. It's this multi-sign, and furthermore, omega itself is changing over time as the unit accelerates. So you can also see friction effects, particularly on the right. And so there's a little bit of stick slip there, which will compound the challenge. Okay, and now to the video that shows what the students are shooting for. So we put between the target and the tracker unit this link. And the plastic block on the left is about 14 millimeters wide. The link has a pin that rides in a groove on the left. And if the student maintains highly accurate tracking, the link stays in the groove. If the tracker has larger errors, then the link will fall out of the groove. And so it makes a very visible effect. It also makes visible and tangible this notion of tracking accuracy. Now, as I mentioned, I fly the unit on the left, and my reference signal gets faster and faster as time goes by. So as time goes by, the reference motions are going to go out of the closed loop bandwidth of the system, or the tracking accuracy bandwidth of the system. You'll recall that students measured that in lab part 5, and so we have a basis for making clear that this will only be able to track for some duration of time. And a final point is we can measure performance then with a stopwatch. And so this becomes a competitive activity. And our experience has been a quite positive response from students. Students are very engaged in the lab. They're very excited to try it, to tweak their controller a little bit, and to try it again. And so I'll just turn on this video, and we can see how my controller performs here. But you can see that it's tracking. The motion accelerates over time. The motion is also not simply a periodic motion, but is this multi-sign motion that has various twitches and jumps. So as time goes by, the tracking challenge increases. We're doing pretty well thus far. And of course, I've seen the final reel. I know what's coming. They will all fall out eventually because it really whips. So there you can see. And I had a tracking performance of about 35 seconds there. Now, I want to speak a little bit more to this belt. Let's see if I have a slide that addresses the issue that I'm moving towards. Well, how do I? Yes, here we go. So we've discovered the following kind of remarkable thing in the stock SRV-O2 setup with the gear drive. And that is that the students are able to realize sliding mode control accidentally. And I want to thank graduate student April Miller for helping me with these data collections. She and I are working on a paper, what we believe will be the first presentation of accidental sliding mode control. And so the case is the following. So in the tracker lab that we were just seeing, students were invited rather, to hand tune their tracker PID controller for higher performance. And what we observed in lab, and this, in fact, we've been observing this since the 1990s, but it wasn't really until more recently that we took time to investigate what was going on more thoroughly. But we found that some students would double their tracking time by tuning gains to crazy high values, hundreds of volts per radian, thousands of volts per radian second. These are values that are 10 to 100 times higher than the values given by PID control design, and yet they got improved performance. And another issue that arises as students would investigate this regime is that nearly any combination of high gain values would work, and furthermore, would work better than the controller design they achieved using root locus techniques in PID controller design. So, and this strikes me as completely the wrong lesson. That is, we've got an entire semester of work. The course is a 4-credit course at UWM, which translates to 12 to 14 hours per week of work. Students are working hard to do this, lots of math to cover. And our final lab, what does it show them? It shows them, well, forget the math. You don't need any of that. Just crank up the gains to really high values, and you'll win the tracker competition. So how do we get sliding mode control here? For those of you familiar with sliding mode control, it's a nonlinear control technique that has pretty wide application in robotics and power electronics and other areas. That's based on saturating a control signal. One instantiates the so-called sliding surface, which is a region in state space, and where the control effort will be 0, and then the control effort is positive on one side of the sliding surface and negative on the other, so that state trajectories converge to the sliding surface. As Slotine points out, Jean-Jacques Slotine at MIT was a pioneer in practical sliding mode control, not the first one to approach the mathematics, but really played an enormous role in bringing sliding mode control to practical applications. The switching surface is both a place in the sense that it's a hyperplane in state space, but it's also a dynamic. So any state which is on the switching surface will converge to the origin of the switching surface. This plot is shown in error coordinates. And I have this plot. This is one of many data sets collected by April. This is a 3-dimensional error coordinates because we have integral error, we have position error, and we have the error derivative. So this is capturing the system as a third-order system, neglecting that resonant mode. And in MATLAB here, we can fly around the data set, but the compelling evidence that we're in sliding mode is the nonlinear behavior characteristic of the response. So we introduce a disturbance that takes the state far away from the origin. In error coordinates, of course, we should be steadily at the origin, and a majority of the points are in a small neighborhood of the origin here. But we disturb the system, and then the system responds. It's able to penetrate the sliding surface down here. It comes back around, and then it's captured by the sliding mode. The light blue lines, the cyan planes, they're actually planes in 3D, are the edges of what's called the boundary layer. So in one formulation of sliding mode control, there's a thin region with linear control action, and Slatine and his graduate students have worked out system dynamics inside of this thin region. But long story short, a properly engineered sliding mode controller will do exactly what we see here. Namely, the trajectory will come, will enter the volume of the boundary layer and then will not exit after that. And this is what the high gain control is doing. An attribute of sliding mode control is that detailed modeling is not required. You just make the gains high enough. And this of course, is just what we're seeing in the lab. The students make the gains crazy high, and then they get good control. So the belt drive, a way to understand why we went to all of the effort to identify a solution of pulleys. The belt is actually an O-ring sized correctly to give us the tension we want to resist slippage. And the belt drive, we went through all those steps to put the belt drive in there to block this controller solution, to avoid this very pernicious lesson that that a semester's work in the mathematics of controller design doesn't actually get you anything. Just crank the gains to the moon. So with our belt drive realized system, here's a root locus plot. This is gains at least an order of magnitude lower than those sliding mode gains, which give us a stable set of poles for the system. The belt drive system, you've got to take the math pretty seriously, and you know, students can turn up their gains a little bit and see the system go unstable very nearly where the theory predicts here with the root locus. Okay, I wrap up with this overly busy slide again. I just want to emphasize the students are constantly taking measurements, of course, and substantially doing system identification as they progress from one lab to the next. Okay, and let me ask if there are any questions.
Thanks a lot, Professor Armstrong. That was a great presentation. I really enjoyed that. As you said, this is now the Q&A period, so please send all your questions in the questions pane, and we'll do our best to address those. So, Dr. Armstrong, I know you've been, as I said in the beginning, you're one of the pioneers, one of our first clients, and you've run this lab for a long time. So how reliable did you find the Quanser equipment?
Oh, very reliable. I have to say it's impressive to me. We bought our first set of 8 motor servos in 1993, and we ran those to 2017. So we got 24 years of use out of them, and thousands of students had the experience of learning more about controls in a hands-on way.
That's amazing. So now you said as well that there's so they're going through 7 labs. Like, how much time do the students need to complete? Because it's I guess a 4-credit course, you said?
It is a 4-credit course, and we were obliged to introduce an extra lab to introduce Simulink, as I talked about. So that's pretty tight. It would be nice to have 6 labs and solidly have 2 weeks per lab, but we make it work.
Okay, gotcha. What would you say is the hardest part for the students, like the most challenging part?
Oh, the most challenging of the labs is definitely lab part 6, where they do the frequency identification, and so it's got the greatest mathematical complexity. There's some complexity to using MATLAB's fitting routine inverse frequencies, which takes that frequency data and fits a transfer function. And there's no controller component in lab part 6. Actually, we've kind of skinnied it down as much as possible. But nonetheless, it remains challenging. It's challenging at a mathematical level. It's challenging in terms of the quantity of data which is involved. And I suppose that reflects reality as well. When you can tune a control system based on transient response, that's a more straightforward approach. And what is it? It's Ziegler-Nichols tuning rules going back to the 1940s is based on transient response. But if you need a fuller transfer function, there's of course a lot more work to get that.
Okay, great, thanks. All right. Well, that brings us to the end of our webinar. So I'd like to thank you again, Dr. Armstrong, for this great presentation. We certainly appreciate it. So, and a big thank you for everyone that attended today. So if you want more information, please visit our website at quanser.com or our LinkedIn page to find out more about Quanser solutions and any upcoming webinars. We're constantly posting stuff on our social networks. And with that, I wish everybody a great day. Thank you.
All right. Thank you. Goodbye.
Bye.